Today we are going to discuss regarding identity-based encryption. So from the previous discussion, it was very clear that the digital certificate is a verifiable way of communicating the public key of a subject. An alternative to a digital certificate emerged in 1984 in the form of identity-based encryption. So it is an alternative way for verifying a public key of a user. So this idea was first proposed by Shamir in his original paper. He used a scheme wherein person's public key could be computed as a function of the person's unique credentials such as his email address. Thus, anyone can reliably compute A's public key only knowing A's email address. This idea of Shamir used RSA-based cryptography, but later Monch proposed the same idea using bilinear pairings in 2001, and it is bit more popular compared to the idea which was proposed by Shamir. First, we discuss regarding how generic IBE scheme works. So, the IBE scheme works as follows. The public key generator, the private key generator has a private key and associated public key parameters. To obtain the private key, the party A informs the private key generator that he or she wishes to receive a private key corresponding to her email ID, say alka@iitb.ac.in. The PKG makes sure that the credentials does indeed belong to, say, party A. The PKG also makes sure that this ID is universally unique. Say nobody else has the same ID. If so, it guarantees the private key of A, which is the function of her email ID, and the private key of the PKG. See, the private key of party A, here it is calculated by using two things. One is the email ID of party A, and second is the private key of the PKG. These two together helps to generate a private key of A. The PKG then securely transmits the private key of A. With the knowledge of public parameters and A's email ID, anyone can compute A's public key. This is how the identity-based encryption scheme works. The previous points, what all we have discussed, it is represented in the form of a figure over here. First, A is requesting the private key using his email ID. So after performing the verification of this email ID, PKG generates the private key of A using his own private key and Alka's identity. So these two will be used for generation of A's private key. So that private key, which is generated by using these two parameters, will be supplied to A. So anyone who knows certain public parameters of A and the email ID, very easily he can calculate the public key of A. So by obtaining the public key of A, the person can send the encrypted message to A. The identity-based encryption idea later on implemented using bilinear pairing. So a bilinear mapping BXY maps any pair of elements from one set to an element in the second set. The term bilinear follows from the following property of mapping. So that is shown over here. So next we're going to discuss regarding the basics of bilinear pairing and examine how they be used to implement IPE. We'll start our discussion on bilinear mapping. In mathematics, bilinear map is a function combining a set of two vector spaces to yield the element of third vector space and is linear in each of its arguments. So it maps any pair of elements from one given set to elements of a second set. This is shown over here. We are talking of a mapping of elements of say one pair of elements to another set. Okay, so this is represented over here in the form of equation. So in this equation, the u1 and u2 and v are the elements of the first set, and k1 and k2 are the integer constants. To understand regarding that equation, let us consider one example. So here we are demonstrating a dot product of two vectors. Using this dot product, we are trying to say establish or try to prove this equation to show that this thing works. So here we have two vectors u and v. Taking the dot product of these two vectors, say u is 241 and v is 532. So when we take a dot product of these two vectors, we get a 24. Just this one is to demonstrate the dot product of two vectors. Next, to understand regarding this bilinear mapping, okay, we'll verify by taking another two vectors, that is u1, u2 and our v. So u1 is 245, u2 is 712, and the two integer constants are k1 and k2. k1 is 3, k2 is 4. Let us substitute these values in this equation. After substituting the values of k1 and the vector u1 and k2 and a vector u2, so and performing the operation of multiplication on these vectors and finding the addition of these vectors, we're going to have this value, and taking the final value, taking the dot of this value and with a vector v, so we're going to get a 364. So this is the outcome of LHS side of the equation. And now consider the RHS side, so where we are talking of taking the dot of u1 and v and u2 and v and multiplying those dot products with k1 and k2 respectively. So first take the dot product of these two. So u and v is 32 and the dot product of u2 and v is 42, and multiplying them with the constant k1. k1 is 3, so 3 is multiplied with the dot product of u1 and v. So and u2 and v dot product is multiplied with k2. So in the end our value is 264. So in general it is ku1 plus k2u2 dot v is equal to dot product of u1 and v multiplied k1 plus dot product of u and v multiplied with k2. The IBE scheme of Bosch and Franklin was the first scheme that implemented IBE. The heart of this scheme is bilinear pairing. Bosch and Franklin scheme uses two cyclic groups, say G and tau, of large Riemann B. The bilinear pairing maps a pair of elements from G to an element in tau. So this is what is an idea they used. So here G is some additive group, has an identity element 0, and tau is a multiplicative group, has an identity element 1, as already we have discussed regarding these groups in module 2, module 1. The properties of this bilinear pairing already we have discussed. So this was an idea that is used in Bonch and Franklin's, say, IBE scheme. In Bonch and Franklin's scheme, once the cyclic group G and tau and the mapping function beta are decided, then the private key generator proceeds to set up its public parameters. Thereafter, the clients may request the PKG to generate the private keys, and on their behalf. First, we'll discuss regarding PKG parameter setups. PKG chooses say generator P of the group, that is G group, and it also chooses a private key, that is some random number, K, small k it is. Say this k belongs to ZP. It then computes the corresponding, say, public key, that is capital K. I'm using the notation capital K for a public key, which is equal to K into P. So this is how the public key will going to be calculated. The PKG then selects two hash functions. The first, I, it maps the person's ID. It may be his birth date, or it may be his email ID. We have taken an example of email ID. This I maps person's ID to an element in the cyclic group G. The second hash function, that is mu, that maps an element in, say, tau to an L-bit binary string. Yes, here L is length of message block. It is length of message block. Now we have two groups. One is G, another is tau. Together with their order P, then these two groups G and tau together with their order, it will be made publicly available. So in addition, the generator of these groups P and the PKG public key, that is K, and bilinear mapping beta, and the hash functions where I and L, I mean to say I and mu are all publicly known. So I list the things which are made public over here. They are, say, two groups, that is G and tau groups. These two are the groups. These two groups G and tau, and the order of these groups, that is
P, they are publicly known. Apart from this, the generator, say we'll use the term small g here for generator G, the PKG public key, that is K, the bilinear mapping function, I'll take some beta because previously I used the term B for bilinear mapping function, so here I'll take it as beta, and the hash functions, they are I and mu. Yes, they're all made public. So the things which are publicly available are G, tau, P. This is small p, which is the order of these groups, generator, public key, and function, and two hash functions. Okay, so after doing all these things public, then users public key and a private key generation we'll discuss regarding that, because this is a public key of PKG. Fine. So now we'll discuss regarding generation of users public key and private key. So let the say say client's ID, I'll talk regarding the ID B, we'll call it as ID A, and client, it contacts the PKG and requests a private key. It requests for a private key. So IDA is the client's ID, and it contacts PKG for its private key. Fine. Then so on the request of IDA, this client, the PKG first verifies its credentials, like its email ID. Say for example, here we are considering a email ID which is used for generation of the private key. So it verifies the email ID. Then PKG computes the public key and a private key as follows. You see, the public key is calculated. I'm going to call this public key as capital A. So this public key is going to be calculated using the I, that is hash function. Okay, the first hash function I, and the ID of the user. Okay, then this is a public key calculation. Next is private key. How exactly private key will going to be generated? That I'm going to call it as alpha. This private key is this equals to a small k into A, the public key of say client, and the small k, that is some random integer which was selected at the beginning. Fine. So these two were together used to generate the private key of A. So now PKG, it will securely communicate this A and alpha to a client. Here my client will go to be A. So this IDA is the identity of A, and it securely communicates these parameters to A. Now we'll talk regarding encryption. Now we'll discuss regarding encryption. Suppose B wishes to send a message to A. B requests, say here party B wants to send a message to A. So what B will do, you know that B will ask for the public parameters, say of A to a PKG. Then B knows the ID. Here we'll start with the assumption that B knows this ID of A, and to encrypt a message of length L bits, yes, this is the length of message. The B will do the following things. First, to start with, B select some random number R, so which is again a part of the ZP, and then B computes the following things, that is C1 is equal to a random number R into a P, random number R into a G, generator of a, say, group, generator of the set G. Then it will calculate C2 M, that is message of length L bits, XOR the hash function mu and bilinear function B, which maps a public key of A and RK, R and K. Fine. So this is capital K. The pair C1 comma C2 is now ciphertext, which will be communicated by B to A. So A gets this ciphertext. I hope it's clear. Now we'll discuss regarding decryption. So how exactly A gets a message? The decryption process is as follows, that is C2, which is part of the ciphertext, XOR mu, then that bilinear function with parameters alpha and C1. Then this will be simplified as C2 XOR mu bilinear function alpha. I'm going to replace this alpha by the values, that is small k and capital A, into C1, that is small r, into generator G. Then again I'll simplify this, C2 XOR mu beta, that is bilinear function which consists of A comma small k r G. Then again simplification, that is C2 XOR mu bilinear function A comma R this is step by step way of decryption. It is C2 XOR mu bilinear function A comma, it becomes kg is capital R, capital K, so I'm going to replace that by capital K and then K. This is nothing but, say, from this it is very clear, it is message. So from this equation, say 1, from equation 1, I'm going to replace this by M. I hope it is clear. So this is how the decryption happens.